So if you look at the formula for the scalar projection is a number. Well, by the way, what is that formula? So it is A dot B, vector A dotted with vector B, over the absolute value of vector A. And as I was looking at this formula and looking at picking out problems for the quiz, I was a little bit confused because of something I said yesterday. Because the dot product could be negative. And so I was like, well, wait a minute. Isn't the magnitude the length of the vector and it's positive? So I found that a little bit confusing. And so I thought about it. And in fact, in the book, I looked up in the book and I saw that the scalar projection is not the magnitude, but it's the signed magnitude, which indicates it could be negative. I'm looking for that little phrase in the book here. Here it is right here. This is just an example of sometimes when you're reading a math book, that one little word you miss could sometimes throw you off, right? There it is. It's the signed magnitude. So then I thought about it, and I said, well, you know, I said this in class. I drew my little picture, and as I drew it yesterday or day before, I said, okay, I'm going to draw A longer than B, and I commented, I'm going to draw it like this because it's more obvious about what we're finding when we do the vector projection, that it's kind of the shadow of B on A, like that. And so I was thinking, well, when would that be negative? When would a negative, when would the scalar projection being negative make sense? And it's when it's this. Here's vector A, and you know what? Vector B is going like this. And then the scalar projection of B onto A would come out this way. And for the scalar projection, I do need the projection vector to have opposite signs from A. And that's when you would have the scalar projection being a negative number, because the dot product can be negative.